When I find my code in times of trouble, friends and colleagues.
So, welcome everyone. For those who didn't see my earlier presentation, my name is Danut Enachioiu. I am a software engineer with Google. This is too loud. Just give me a second. Okay, I think this is better. So I'm a software engineer with Google. I've been working for Google for 1.5 years. Before that, I used to work for Microsoft. I worked there for 3 years. I was developing SQL Server. And this is actually quite relevant because today we're going to talk about databases. Now, before I go into the actual presentation, I just want to make sure you guys know what you've signed up for. First off, who here has heard of Spanner? Like knows what Spanner is, at least in principle? Got one? Two? Did I see it too? Oh, great. No. That is something. Good. So what I want you guys to understand from the beginning, Spanner is a database system that is used internally at Google. It's not accessible to external developers. It's not open source. You can't just go and download it. So from a lot of points of view, this is the opposite of my talk in the morning. While that was very focused on here's something you can go ahead and do and use today, Spanner is not that. This is more about here's something interesting that we did at Google, and you might enjoy hearing about it because you enjoy thinking about databases. That being said, if you feel like this is useless to you, like if you're looking for the actual results and something you can go ahead and use tomorrow, this talk will probably not be it. So just disclaimer, if you now want to go, that's also perfectly fine. I'm not going to keep you here. So this talk I had less time to prepare for, so I'll once in a while have to take a look over my notes. We'll see how that goes. So let's get back to Spanner, right? Spanner is a database, and it offers, well, what you would expect from a database. A relational model. You have tables, you have columns. You can query it with SQL or something that is close to SQL. You can make transactions on it. Here's what's interesting. Spanner does actually offer full ACID compliant transactions. Okay, who here knows what ACID is in databases? Great. That's quite a few people. So what does the A stand for? Atomicity, right. So the property that when we do a transaction, it either completely succeeds or it completely fails. It doesn't in between anything. What does the C stand for? Consistency. Right. So this means that basically the transactions should behave as if, when they happen simultaneously, or multiple transactions happen simultaneously, they should behave as if they happened one after another in some order, where the order doesn't necessarily need to be any particular one, but there needs to be that order, right? And it also means that, well, I think that's actually isolation. I think I got that wrong. No, consistency is about the database should never be in a state that is not internally consistent. So let's say you have a database rule that says these fields should never be above 0 or below 0 or something. However you do parallel transactions, and whatever happens with these transactions, the guarantees of the database should never be broken. Isolation was what I told you previously, which is the transactions should seem to happen in a certain serializable order, right? And D, durability. So once we say that a transaction has committed, it should not be easy to lose. Now, it's never going to be perfect, because at least if you have a single machine and it gets hit by a meteorite, we're going to lose that transaction. But barring that, we should probably not, like, the transaction needs to hit disk and be on non-volatile media and kind of be durable, right? So Spanner does all this, and that's not very impressive until we get to the next point, which is Spanner is a distributed database. And let's go for a second into how distributed this will be. So let's say we want to, I had a marker here. Let's say we want to build a database to power a social network, because social networks are cool and everyone's building one, right? So we want to power a social network. We plan to have tons of users all over the place, right? So whatever database will power this, not only does it have to be on multiple machines, but it has to be on thousands of such machines, maybe a lot more than thousands, right? And because our users are going to be all over the planet, we don't just want to put the database in, say, San Francisco, because then everybody else will have a horrible experience in terms of latency. So we want to have this database all over the planet. So it's something like 4 continents and maybe 20 data centers and thousands of machines in each of them. So that's the scale of distributed we're talking about. It actually can scale to a lot more, but let's think about this scale for a second, right? So why is, the tricky part about doing a high performance database in such a distributed environment, out of those transactional properties we mentioned, is keeping consistency. And why is this important? Let me give you an example. People might think, well, do I really care if sometimes I can see an inconsistent state of my database? It's a social network. How bad can it be? What's the worst that can happen if we see a slightly inconsistent state of the database? Let me give you an example. And this is, you have to keep in mind, people use your products for all kinds of things you don't expect them to. So let me give you an example. We have a user, X, right? And this user lives in a country with an oppressive regime, right? In a dictatorship. And, well, he's on the social network and he has a friend, Y, right? So he decides to make a post criticizing his government. Okay. He writes this post. He doesn't click post yet because he realizes, wait, my friend Y works for the government. If I post this and he sees what I posted, I'm going to get in a lot of trouble. So what he does is first this is his list of, let's say, X's friends, right? And then we have also X's posts. Initially, he has no post. So what he first does is he goes and says, okay, I'm going to click around and I'm going to remove X from my friend list. Right? Sorry, Y, right? So then he goes and removes Y from his friend list. And then he goes and posts his new criticizing post, P, right? So this is what happens. He removes Y and then he posts P. So what he did is perfectly fine. Now, keep in mind that when we go ahead and query this database, this Y fella, he might be in a completely different part of the country, hit a completely different database server in one of those thousands of machines and so on. And it's really important that when we compute the posts that Y can see, we don't generate something like this, Y and P. So we don't say, oh, who is X's friend list? Oh, it's Y, because about like 2 seconds ago it was Y, so we're slightly inconsistent, but who cares, right? And what are X's posts? Oh, it turns out this guy, okay, so it's like this. It's just a few seconds maybe of inconsistency, but it matters. In a scenario like this, you can't have eventual consistency, right? Eventual consistency is what most highly distributed databases offer. If you look at, well, I wouldn't call it a database, it's essentially a key value store, but Bigtable. Are you guys familiar with Bigtable? Bigtable. Let's get some Bigtable's numbers. Okay, good. So a few of you have heard of it. Bigtable is this key value store developed by Google. There's a paper on it. It's not open source, but it was the inspiration for most of these NoSQL approaches that are appearing everywhere else right now. So Bigtable across data centers offers eventual consistency, which means given some time, every replica anywhere in the world will get to this state. But in the meantime, this is possible. And yes, in practice, this meantime might be seconds, but in an exception, it might be minutes. And in those minutes, somebody might see this. So when you deal with things like security, because essentially, a friends list on a social network is security, you really want perfect consistency. You want, if the user does this, it should be impossible for anybody to see this. Right. So, by the way, I will say this again, as with the earlier talk, if you have questions, ask them right away. I hope I know how to answer them. If I don't, I'll try. So we'll see that. Okay, so let's go. How would we actually do this? Like, let's talk a bit about how we would do this. Well, actually, we don't need to erase this yet. If we had a single machine database, right? This is our database. You guys can see because of this, right? It's okay, right. So you have a database, and it gets all these incoming write requests, right? Some of which are, whoa. Can we, no. Thank you. Because I want to see them as well, not just the light. Okay, so you got all these write requests, and we need to kind of read this database throughout, because we're trying to build this model of what posts we should display and so on, right? So we're trying to read the database from top to bottom, because let's say that's how we implement this query. And we want it to be consistent in the face of all these writes. What can we do? Ideas. Come on. Oh, come on, folks. Don't be shy. You have ideas, I'm sure. How about if we just stop all of these, right? Like we could say, well, we're going to start computing the list of posts. And while we do this, database, please stop writing. Just finish your current transaction. Let's now read everything and now continue putting transactions in. This obviously works, right? Because if nothing is being written, it'll be perfectly consistent. But if we do this, the performance of this database will kind of suck, because every time we need to compute somebody's like view in the social network, we would have to stop every write, every post, and so on. So at a big scale, this doesn't work. This doesn't work. A different idea that ends up being used in most modern databases is called snapshot isolation. And what this means is, before we start computing this, we make essentially a logical copy of the whole database at a given moment in time. So we say, okay, this is our moment X, time is something. Everything that is written afterwards, we write in such a way that we can tell that it's been written after X, right? And then once we've chosen this model, we can go ahead and do our query here. And wherever this X comes, it will be consistent. Like the X might be here, it doesn't matter. It'll be something consistent. Right, by the time we finish computing this, maybe the user has reached here and we're computing with this. That's fine. It'll be slightly out of date, but consistent, right? Which is more important. So we can do this. It's nice, but that's a single machine. What happens if we want to do this for two machines, right? We have this database is kind of distributed between two machines, and these writes are happening all over the place. And again, we could lock everything, but that's even worse now, because now we're blocking two machines just to read one thing. And we could do this, like make a copy of this one at time X, right? And make a copy of this one at time X, like a logical copy. It doesn't have to be copied completely, the data. It can be done smarter than that, right? So we make these copies and then we run over it. Is this sufficient? Really, because it turns out this copy needs to be consistent with this one. So think about it this way. If some transaction was happening both here and here, it shouldn't be committed just here and not here and so on. So like the two servers need to agree very exactly on this X moment. Like they should think of X as exactly the same moment in time. And now if you try to expand this to Spanner and you go to thousands and thousands of machines across a lot of continents and whatever, no way you're going to have machines that can perfectly agree on a moment in time. So that doesn't work. So we're going to do something different. Okay, let me see if I missed anything, but hopefully not. Right, so one thing you have to keep in mind, which kind of enables this, is that Spanner is a multi-version database. And by multi-version, that means that when we have a field X, right, in Spanner, it doesn't just have a value 2. No, it also has multiple values, and each value has a timestamp. So we're going to say x was 2 at moment 0. It was 8. Well, let's make this A, B, C. So make it A, B, C. It became B at moment 5, and it became C at moment 27. Right? So that means it's pretty easy for us to do a snapshot query. So it's pretty easy for us to compute, hey, what was x at moment 7? Well, it was after this, before this, so it must have been B. So this is pretty good, right? The problem is, how do you assign these numbers in a way that is consistent across machines, across data centers, across everything, right? And let's go to, yeah. No. So, on a single machine, if we wanted to assign these timestamps correctly, one very common algorithm that is used for ensuring consistent transactions is called two-phase locking. And the way this works is you have a transaction, right? And the name is kind of misleading, so ignore the name. You have a transaction. The user says, do this change, and here's where the change completes, right? During this time, what happens is first, the database up to a certain point acquires locks for all the data that it intends to modify, right? And there's a certain moment here in the transaction when now we have all the locks. Then it goes and does the actual work, right? Work, whatever, makes the changes required. And then there's a moment somewhere here where it releases all these locks because it completed the work, right? Simple enough. Now, this guarantees serializability and guarantees all the consistency properties you want, because it's, if you think about it, this means that in any situation where the same data would be affected, the transactions need to have a very clear order, right? Because this interval cannot overlap with another transaction that affects this data. So one way or another, this would order transactions correctly. So this is very easy to compute in this case by just like choosing the right timestamp is very easy by just choosing any moment within this two. And I'm going to show you why this is correct and why this is actually provides something called external consistency, which means it's actually a bit more than serializability. It means that any observable way from outside the database of telling in which order the transactions happened will match the order of these timestamps. And I'll give you an example of that, right? So how can we tell from the outside that two transactions happened or seem to have happened in one order or another? Well, the first option is they're actually clearly separated, right? When you take a database, let's go here. You take a database, you have two transactions, T1, T2. And this is time, right? This one happens from here to here, this one from here to here. No database will guarantee to you what order they happen. Just because this one started later doesn't mean that this happens second. The actual moment when the transaction is, committed and worked on might be here for this one and here for this one, and that's perfectly fine. So in this kind of situations, from the outside, you can't tell in which order they happened. But if I have T1 from here to here and T2 from here to here, right? So T1 finished before we started T2, then as an external observer, I am sure that this is the order in which they happened, right? It's pretty clear. So obviously, if we choose a timestamp within the lock and release areas for each of these transactions, however we might choose these timestamps and however these areas will be, the timestamp from here will be smaller than the timestamp from here. So in this case, it's obviously correct. What if they're overlapping and they actually touch the same data? So let's say we have these transactions here. We don't know if the moment is here and here, right? We have no idea where it is. We have these transactions here. And this transaction writes, let's say the purpose of this one is to write A equals yes, right? And this writes A equals no. Now, we can't guarantee the order by looking at the moments and the timings, but if at this moment afterwards, if A here is yes, then it means this transaction was first and this transaction was second. If A here is no, it's the opposite, right? So, respecting external consistency means that the timestamp of this transaction and the timestamp of these transactions should match whatever the result is here. So the one that has a later timestamp should win. With this approach of grabbing locks and taking any timestamp in the middle of, like not in the middle, it can be anywhere during the time we had locks, this will work. Let's see why. Let's say that's this order, right? And locks are from here to here. And we take this timestamp. Then this transaction modifies the same data as the one before it. So it can't overlap the lock release area with this. So it needs to either happen before the lock or after. In this case, it'll probably happen something like this, right? Lock release. And any way we choose a timestamp in here, and any way we choose a timestamp in here, the order of the timestamps will be correct regarding who wins. Right? So this seems pretty obvious so far. It's like, yeah, that makes sense. But where's the trick in this? Well, why don't we just do this? Like, take your computers, take timestamps like you said, and suddenly you have perfectly good snapshots and transactions and consistency and everything. Well, the big difficulty is taking this timestamp. Because, see, we don't actually know what time it is. So we have our transaction, right, running on some machine somewhere. We've grabbed our locks. And now we want to find out what time it is. How do we do that? We ask some kind of time function, right? What's the current time? But that is not perfect. Our computer's clocks are not perfect. You can't rely on this clock telling you exactly in an absolute manner that what time it is. Because think about it. The essential part is that if we pick this timestamp here and this timestamp here, which are really close by, even if they were picked in completely different computers across continents, they should still be in this order. And you can't actually guarantee that with computers. With enough transactions and with enough speed, this is not going to work. It's not going to work. So here's what Spanner does, and this is one of the biggest, interesting things that Spanner brings. We created an API called TrueTime. It's like camel-cased TrueTime. And this TrueTime API, you ask it what time it is. And it tells you what time it is. This seems pretty boring, but it doesn't tell you it's this moment in time. No, it tells you it is between here and here. So it says it's the earliest time that might be now is this, and the latest time that might be now is this. As in, it reifies uncertainty, clock uncertainty. Not only does it tell you, of course, any API for time approximates what time it is. But this one actually tells you, the approximation, tells you it's here plus minus an epsilon, right? It's somewhere. We're somewhere in this interval, and we could be anywhere. I'm going to go afterwards into how we get this data, like how this API works. But now, for a second, assume we have this. How can we actually pick a globally consistent timestamp for every transaction? So take our transaction again, right? Just make it a bit bigger. Grab our locks. And now we ask TrueTime, what time is it? And TrueTime is going to say, well, it's between this and this. I have no idea what time it is, but it's between this and this. So the interval that TrueTime might give us might be like this, might be like this, might be like this, might even be like this, right? Like it's guaranteed to contain the correct time here, but it might be before, after, and so on. So out of this interval, we choose the only value that is guaranteed to be after we grabbed all locks. Which value is that? Yes. It's like the latest value, this one. Because, see, look at the intervals again. No matter how I scroll it, so it still contains this end is always inside. So it's guaranteed that this is in the future, or it is exactly now, but essentially in the future compared to this one, because our true time call will actually happen slightly after, right? It's not instantaneous. Right, so we choose this moment. We choose this as our timestamp. So far, so good. Now, the problem is we would now have to release the logs here somewhere, right? How do we make sure that we haven't chosen a moment that is after this release? Because if you choose your timestamp here, everything we talked about, all these awesome properties, doesn't work anymore. It needs to be between lock and release. So how do we make sure we don't do this? Exactly. We wait. It's nothing very fancy. We wait. So let's say around here we ask, we chose this moment, right? And we ask true time here, hey, what time it is? And true time says it's between here and here, right? It's actually here, but true time doesn't know exactly, so it says this. Can we release the locks? No, because we might be here. It might be too early. So we wait some more and ask again here maybe. This is implemented smarter than that. It will not poll every millisecond, hey, are we there yet? Are we there yet? No, it won't. It'll do something smarter. But this is the basic idea, right? So we wait for true time and how do we guarantee? Like we just check that earliest, according to true time, should be after the moment we chose the timestamp, right? And then we release our logs, and that kind of guarantees that the timestamp we chose is within the limits. There's a couple of other notes here on how this will work in a group, but never mind. This is the basic idea. Now, this might seem a little bit wasteful, because you're going to say, well, then you always have to wait this uncertainty. And by the way, the typical uncertainty we see in production is an epsilon of less than 5 milliseconds, right? So that means that this wait, if you look at it, the typical wait will be 2 epsilon. So it will be typically around 10 milliseconds. But this typically actually doesn't matter. And you know why? It's not because we don't care about 10 milliseconds. Like, we do care about 10 milliseconds, that's sure. But we don't care because, remember, we were not just doing this for the exercise of choosing a timestamp. We actually have a transaction to do. And it turns out that, you do the transaction during this time, and it typically takes something comparable to 10 milliseconds. Why? Because as a distributed database, so I haven't gone into this because it's... Okay, side story. I think we have the time to go and do this one. So the idea is, yes, it takes around 10 milliseconds to do the actual database-y stuff, right? And so this wait is not so harmful. Before we go into actually how we compute this interval, which is pretty interesting, let me tell you an interesting story. You guys all know what a database is, right? So I thought so too. Until one day, I was in my home university. It was like 10 years ago, 8 years ago, something like that. And I go to this office, which did some administrative task. I don't remember what the task was. It was something with administration and, paperwork and whatever. So I asked what I wanted, and there's 2 people in the room. And it's this lady and this gentleman. And the lady calls him and says, Mr. whatever his name was, could you please check in the database if this is registered? And I go, whoa, database. Look around. No computers. Wait a second. Database? Look around. Okay, well, maybe he's going to go in a different room. He doesn't. He actually stands up and goes to this little metal cabinet. And I'm like, okay, there's a computer in the cabinet. He opens the cabinet, no computer in the cabinet. And then he pulls out this big, fat file, and he pulls it out, and on the file, with big letters, it said, the database. It was actually a pretty scary moment. But the point is, there's nothing about databases that make them be something necessarily related to computers. And I think the best proof of that is the Paxos algorithm. Anybody here familiar with Paxos? At least vaguely. Heard of it? Heard of it. Awesome. So the Paxos algorithm, so Paxos was this island. It's a Greek island, and they had a very, very successful civilization a couple of thousand years ago. And they were traders, right? But they were traders, but at one point they figured they liked democracy as a thing. Hey, democracy is interesting. But nobody was willing to invest full time into becoming a senator or somebody who takes care of laws and things like that, right? And votes and so on. So they had a parliament where people went in and went out of the parliament at all times. They didn't even have like a secretary that would take down all the laws. Now how it worked is each of them had this big register in which they could write the laws that they pass, right? And they would have a sequence number and so on. But none of them would be guaranteed to be present at everything, right? Some guy felt like he doesn't want to do this law thing for 2 days. He didn't, and so on. So they figured out a protocol. And this is no joke. I mean, you read this and it sounds as one of those, very artificial scenarios that an informatics teacher comes up with to explain something crazy. But this is not. They actually came up with a protocol where they could have consistent registers that had the same transactions, not necessarily all of them, but they never had conflicting laws in their registers. And it worked while people could come and go out of the parliament at all times. And this is a very similar problem with distributed databases today, right? You have all these machines everywhere, but they might crash, new machines might start, network connections fail, network connections come back up. So you have this pool of machines that always, comes back up and leaves and so on. So the Paxos protocol is actually very good even today, and it works very nicely. I won't go into details on how it works, but I strongly recommend reading the paper. It's called, let me write this down as well. It's called Leslie Lamport, The Part-Time Parliament. This guy is an archaeologist with a hobby for computer science, and he explains mostly what the Paxonians did and what their reasoning was and how they came up with this algorithm. But he also explains it in a mathematical and computer science view as well. It's an extremely interesting paper. It's one of the most interesting things that you'll get to read, just because it's something that actually happened 2,000 years ago. And they solved most of the distributed databases problems that we have today. They figured out something for them. Load balancing and consistency and pretty much everything you want. Snapshot is isolation, leader election, every problem in distributed databases, they hit at one point. Right, so Paxos essentially relies on having a group of machines vote together on whether a transaction succeeds. And when you have a majority of machines agreeing, then the transaction is, let's say, irrevocably committed. Very simplified view. The problem is, because this involves more than one machine, and sometimes it involves machines in different data centers, this process, which happens here, can easily take 10 milliseconds. So this was kind of a sidetrack conversation, but this is why 10 milliseconds doesn't really matter. And now let's get to kind of our last part, which is how does true time work? How do we actually know the incertitude here? So how it works is, first off, we have a bunch of machines, servers at Google, that know what time it is with very, very good precision. And how might we do that? Come on. How can we find out what time it is? Very, very precisely. Sorry? Indeed, atomic clocks are one of the things we use. So some of them use atomic clocks. which are not nearly as scary as they sound. Nowadays, they're essentially this little board you put in the machine, and it's not even that ridiculously expensive. And atomic clocks are, yes, used quite a bit. There's also a different source. What? GPS, exactly. Do you guys know how GPS works? Like just how... So you do know there's all these satellites circling the Earth, and they somehow communicate to your phone, and your phone figures out where you are. What do the satellites send? Exactly, the time. This is how it works, essentially. They all have an atomic clock on board, and they send the time that is on them. And because of the delay, you can kind of compute where you are, because you can compute your distance to the satellite pretty well, knowing what's the difference between the time they send and other satellites and so on, right? It's a lot more complicated than that, but essentially any GPS signal contains a very exact time signal, right? So we have GPS. So we have some of them with GPS, we have some of them with atomic clocks. Why do you think we have both? No, see, the GPS does use atomic clocks, but those atomic clocks are on the big satellites. And they're significantly more fancy than the ones we use. I mean, those are huge atomic clocks. But that's not, like from our perspective, that's not the reason. The reason is these things kind of fail, but for separate reasons. So for instance, GPS will stop working if it's extremely stormy outside, right? If we don't have good satellite connection, GPS will stop working. GPS can also be quite easily jammed and intentionally or not. So this has happened. You can actually fake GPS satellite signals and kind of skew clocks and so on. And this does occasionally happen. Atomic clocks, on the other hand, they don't rely on the weather. They can't be externally messed with. On the other hand, they do have a small drift by themselves. I mean, our atomic clocks are not, the reference time for our planet is done by an atomic clock, but that atomic clock is way bigger than what we use. These ones do get slightly out of sync with time, so they do need synchronizing once in a while, where kind of GPS comes in. We would not want to run on just atomic clocks for, say, 2 months, because things will be slightly skewed. It's scary that matters, but it does. So we have all these machines with atomic clocks and GPS, and what we do is that every server, every machine we have in our clouds, synchronizes with these and finds out from these what time it is. And this uses a version of NTP. Are you guys familiar with NTP? Right, it's a time synchronization protocol for a network. It's basically an implementation of Mazzullo's algorithm. The basic idea of how this works is you first measure kind of how good the network is with a server and figure out what the error rates are against each server, and you kind of get an interval of time from each network source. You don't just ask one server what time it is. You ask multiple ones. You get this interval, and kind of looking at it, you figure out some time around that where they all seem to kind of agree. Yes? No. Right. So we use something like this, and we synchronize the clock with these. And our algorithm that does this also computes what the error is, right? And what do you think, like it might decide it somewhere between here and here. What do you think are the sources of error? Like what causes this error to appear? So for one thing, it's the original source, like they have a little bit of epsilon as well. They're not perfect. But this is actually less meaningful than the network time. Communicating with servers that are farther away means a bigger error. We've actually seen this in production. At one point, we had time masters in the servers that have atomic clocks or GPS are called time masters, and we had time masters in one cluster kind of go offline, and all the computers had to synchronize in a different data center. And because of the extra delay, we immediately saw much higher epsilon values everywhere. And this is expected, right? So it's mostly because of network time. Now, each of these synchronizes to a certain value, but how do we keep this? Because we can't continuously and instantaneously synchronize over and over. It doesn't scale, right? Because this synchronization takes a while and it's kind of bad. So what we do is we've measured the properties of the clocks on the built-in clocks on the machines that we use, and it turns out they have a very well-defined maximum drift, right? So given 1 second of real-time passes, these clocks will usually do, I think it's something like 6 microseconds per second or something like that. It's a very small number. I forgot what the number is now, but it's actually pretty small. But we account for it, and between two synchronizations here, this interval slightly increases, right? We actually do synchronizations every 30 seconds. So every machine in our clusters synchronizes with the master machines for time every 30 seconds, but still between those 30-second synchronizations, the epsilon that this machine reports grows slightly bigger. And this is basically how true time works, and how exposing the fact that we don't know exactly what time it is, but knowing how inexactly, allows us to do pretty amazing new things. Spanner is actually used right now. Most importantly, it powers F1. F1 is Google's advertising backend, so the database that does everything about Google advertising in Google search and so on. It's, as you can imagine, it's huge, and it has enormous numbers of transactions per second, right? And it's all powered by Spanner, which is pretty awesome. It's also used for a couple of other projects, but they weren't announced yet. I recommend, if you're interested in it, this was kind of a skim through of the topic. There is an academic paper published on it called Spanner, a distributed database system something. Just look for it. It's available on research.google.com. It's there, and go through it. It's a lot more depth than this, but very interesting to read. That's it. Thank you. So, anybody has questions? And again, I'll try to answer it, and I'm not sure I can, but go ahead. You could ask, when can we play with this? Hey, see, exactly. That's exactly what I said. I have no idea. I literally have no idea. It was not designed for that, and it was a lot of work. This was something that Google worked around 5 or 6 years on. So the basic ideas seem pretty simple, but much like many other Google technologies, the devil is in the details. Actually implementing this correctly, functionally, and making it fast for a real-world huge database like F1 was very hard. So I'm not sure if or when it will ever be available to external developers. But the algorithms and this part, and actually a lot more than this, have been made available so the scientific community can actually use this already. So if you read the paper and kind of look at how it works, you can implement something like this for a toy project, just to test something, or for academic purposes. You can do that. You can follow the paper and kind of get something working. From that to something that you would work production-wise, it's a big road. Yeah. I mostly don't know. I know that it's used. It was announced as being used for F1, and it is used for F1 even now. It's used for a couple of other things that I know of, but they were not disclosed yet, and I can't tell you. But you can imagine that a lot of people at Google are excited to have this, because this is in many ways kind of a holy grail of databases. Like having a relational perfectly consistent global transactions database that distributes everywhere and is fast. Because you see, we also had Megastore. Megastore is another database that was like there was a paper published on it, so you can also read about that. It's based on Bigtable, and it offers consistent transactions across data centers, which is great, but it does so by limiting you to about 1 write per second, which is especially around the same records, which is quite bad. You don't want that. Yeah. It's not. It's the Holy Grail only. No, I'm kidding. Okay, I don't know what you mean, but go on. Mm-hmm. Spanner does all of them. I mean, it will never be as fast on micro benchmarks as a single database that runs on a single machine, right? That'll not happen because but you do get extra value on top of that, because unlike a single database running on a single machine, Spanner can't lose data by just one hard drive failure or whatever, one machine failure, right? So it'll never be as fast as that, because yeah, it involves some network communication and so on, but on the other hand, it does kind of offer all of these things. You get consistency, you get distributed. It's not. It's actual real consistency. So when your transaction comes back as success, then you know that any request anywhere in the world will be returning the new value. And that's pretty good. The idea of why we wanted to do this, I mean, you can write applications that work with eventual consistency and be quite successful. A lot of internal Google applications use Bigtable as a storage system, and Bigtable only offers eventual consistency, and yet we've always found ways to go with that, like to actually still get the correct behavior and so on everywhere. But for the developer, it's a lot easier to think in terms of real consistency than eventual consistency, because you just, yeah, okay, we committed that transaction, it's fine, we're good, let's go, right? Hope that makes sense. Okay. Sure. That's an interesting question. The question is, just so we have it on the recording, is if it's so good, will Google use this for every product or everything? I don't know. Of course, there's a lot of existing investments, and there are things that it does worse than Bigtable. For instance, Bigtable is very free-form about, I don't know, you could do this in Spanner as well. Probably not. I mean, first off, it's a database, and a database is not always the best storage system for applications. For instance, I worked on this application that actually had a completely configurable meta model, right? So this means that you had data in some rows, but the fields were configured at runtime. And the data types are also configured at runtime. And you had a different set of tables and whatever that describes the model, right? If you have something like this, a database in a traditional sense is not actually your best choice. Because if your database looks like object ID, key, value, if this is how your records look in the database, then you're doing it wrong. This is very bad for working with databases like this. Then you might as well just better use a key value store, Bigtable, or whatever, data store on App Engine, or any other of these NoSQL solutions. So databases are not always the best way to store things. I don't even know if I was doing an email system like Gmail, I don't know what Gmail uses, but even if I was building one, I don't know if a database would be the best storage system for it. So I guess the answer is, we'll see. It mostly is. So we found that people have difficulty working with these key value stores. I mean, developers, right? It's still the model of the database, the traditional database with tables and columns and rows and so on, is still easier to kind of work with mentally. And that matters because people are more productive this way. So it mostly is, it supports a subset of SQL. It supports joins to a certain extent, not to a very big one. It also does something very smart around data locality, which is, the idea is you can create these hierarchical tables where you say, well, let's say you have a user table, and then you have a song table, because it's about, you have the songs of each user. You're building Google Music or something, right? And you have a user table and a song table. You can define a parent-child relationship between them in such a way that when it's actually stored, when the data is actually stored on disk, it'll be stored on disk or whatever. It'll be stored something like user 1, and then user 1 song 1, and then user 1 song 2, and then user 2, and so on. So it'll be interleaved, which typical databases don't do, but this actually helps a lot with performance in most real-world web applications, because it's most likely that you want to read this kind of about the same time when you want to read this. And these things are usually modified together, and these things are usually read together. So it makes a lot of sense to put it like this on, in the actual internal representation. But from an external point of view, it looks like mostly like a SQL database. Yeah. Cool. Well, if that's all. I'm not sure what time it is, but if we're early, that's even better. We are perfect. It's 3 minutes to 2, so perfect. Thank you all. And again, if there's more questions, not like I can share a lot about Spanner, but if there's more questions maybe about any of these topics, my email is danut@google.com. Just shoot me an email, and if I don't know what the answer is, I'll try to connect you to somebody who does. So we'll do that. Thank you. Thanks again.